Hello and welcome to lecture 19, part two. If you remember, we started this lecture on Tuesday. We talked about power and design exploration. So we managed to get through the power portion. So now let's talk about design space exploration, right? So imagine you've built your spiffy generator, or perhaps you're still developing a generator. How are you going to go about uh, navigating the space? So, in particular, how do you pick the right design? What metrics do you use to define what is the right design? And then at some point, as you're going through all this process, you're going to realize shoot, we're doing trade-offs. I need to consider multiple metrics at the same time. How do I optimize multiple metrics? So I'm going to cover all these things today. So it's a little bit abstract, a little bit concrete, and show some examples. Cool. So how might you evaluate different designs? Well, you can imagine all sorts of metrics, right? Uh, you know, in the prior few lectures, we talked a lot about PPA, power performance area. So obviously, those are all really important. But even those metrics on their own aren't just a single number, right? For power, depending on your design. Are you worried about your average power, the peak power, energy efficiency in general? What is the issue you're worried about? Maybe about peak thermal in some location, delivery constraints, delivery jitter. What exactly are you worried about? For performance, you're worried about the latency of your thing to compute one operation. You're worried about the throughput. Obviously, many nuances of the performance. And then area, which is kind of our notion of cost, right? Talking about the silicon area on a die, talking about the number of I/O pins, other components, perhaps, option memory components you require. So there's many metrics you can consider there. And you can see in this slide, I've listed all sorts of other metrics, right? And some of these are a little bit harder to quantify. For example, maybe usability, like what fraction of cases can your design handle? Security, which of course also is hard to quantify at times. You can check for specific attacks and specific robustness, but still, how do you kind of quantify and measure that? And then things we don't talk about much in this course, but matter a lot in the real world. Things like manufacturability. How easy to make this design? How testable is designed, not only when developing it, but also actually when you've manufactured it before you put it into a product, you want to test it. Designing for test or DFT is a really important thing in the real world. And how does that your design choices here impact that? What about fault tolerance? What about reusability? So these are all things that kind of put down as a list. You may have even more metrics, but I'm kind of showing this to realize yes, in the real world, you have designs there's so many ways to evaluate them, so many different metrics to consider. And throughout these metrics, you may figure out some of these are things that are nice to have, absolutely critical, or have some sort of constraint. Like you need to reach a certain threshold on one of these metrics. Are there any metrics people can think of that maybe we forgot to put on this list? I can think of at least one newer one. Yeah, I think an interesting point. Okay, so as you're optimizing for a certain target technology, that's a good point. And you kind of have these things. Yeah, so right, these set of metrics kind of in a way implicitly assume a certain technology target, but you can imagine that it's a two-way street, right? How does impact other possible metrics or considerations? Marketability might be below or above the pay grade of engineers, I guess, but that's a reasonable thing to consider. How about in 2025? What are we worried about a lot involving the world? Climate. Yeah, well, tariffs is another whole other metric, right? Which I don't even know how to get into that one. But what about climate? Yeah, so usually we're thinking about the climate sustainability. So I'll put it as sustainability, but you can imagine things like what is the embodied cost of manufacturing this, right? Embodied carbon, right? In other words, how much carbon to make your chip? And if you change your design, chip design, you actually can change the amount of carbon it requires to make your chip, right? So yeah, yes, yeah. So supply chain tariffs, yes, I think you're right to say those are going to manufacturability. Those are real concerns, right? Um, when someone talks about, like where is an iPhone from, right? If you track down every part in that phone and every material to win every part, it'll be a lot of countries, right? It's not just one country, right? And so, yeah, these are important concerns in the modern era. But today we'll focus on the more quantifiable, more engineering controlled metrics. But yeah, it just kind of gets people aware of the fact that a lot of things considering evaluating your design. And so then, so okay, so on one hand, you have the metrics, so how you score how good a design is, right? On the other hand, is what are your knobs you can turn to explore a design space, right? With generators, you can now more easily generate different design variants, right? That's the whole point of generators. So you have external parameters like, what interfaces my module have, what kind of these things. These are things that are visible from the outside of your generator. There are also parameters that users give to your generator, but the generator's external appearance does not change, but it does change internal things, like the microarchitecture, right? Things like how much parallelism do you have internally, or what approach you're using, what routing algorithm you use internally, whatever, right? And so these internal parameters, external parameters, they both are parameters, but the result is that there's a lot of knobs, right? That's the challenge we want to talk about is, given you have a lot of knobs, how do you turn them correctly? So, number one, you know metrics, right? If someone just says turn a knob to get a good design, you're gonna say, I need to know what good looks like. That's where the metrics come in. But then it's also a matter, you turn the knobs all the way, there could be too many combinations, right? So how do we go about turning knobs in an intelligent manner? So let's talk about both of those things to try to tame this design space. So first, for the metrics, like I said, I listed, 10 plus metrics on the prior slide. You should ask yourself for your application, which metrics are truly necessary, right? Or there's some you can just, what, for now we're going to ignore it, we're going to remove it, we're going to, not pay attention to it. Um, and the metrics, let's say you determined, of the original 12, maybe seven are necessary. Is every single one a metric you need to maximally optimize? Or are some of them so you can just say it's a constraint, keep the power under 1 watt and then we're happy, right? Beyond that, it's not needed. Just make sure it's below 1 watt or you make sure, it has some other constraint, right? And so you can start off with these lots of metrics, start turning some metrics into constraints. And then when you get to a point of, maybe only a handful of metrics, let's say two, three, maybe hopefully not more than four metrics you're trying to optimize, is there still some sort of way you can rank them, right? Because you have four metrics you're trying to optimize at the same time. You can make progress that way, but it's also tricky, right? And so it's easier if you can say, you know what, I want to optimize this metric first, and then if any remaining ability, optimize another metric second. It makes your life so much easier. And sometimes, optimizing multiple metrics simultaneously, and there is no precedence. You're going to need something called trade-offs, which are common throughout engineering. We'll come back to them in a few minutes. It's a really common key thing to think about. But even though we're good at trade-offs as engineers, we would love to do everything we can to reduce the number of things we're doing trade-offs amongst, right? Rather than doing a eight-way trade-off, we want to do a two-way trade-off. And so we'll see what it looks like in a few slides. But yeah, so number one, try to shrink the metric space, right? Which metrics are really important? Because the metrics we turn into constraints rather than things to optimize. And then even the ones you're optimizing are some more important than others to kind of get that precedence order. Okay. Then for the actual design space itself, um, like I said, the problem is there's so many combinations of parameters that you end up with a design space you can't explore fully, right? And so how do you do that intelligently? And so sometimes with some expertise on the problem in your generator, you can recognize certain things. For example, let's say you have two parameters, they each have n settings. Are they really fully independent? If so, that means you have n squared combinations. You got to check all n squared combinations. That's rough. But maybe you know what? I changed this thing. The other thing is going to directly depend on it. And so really they aren't truly independent. They actually are a coupled parameter. You can imagine maybe something like, queue depths, right? I have a queue depth in one location of my design and then another location of the design. And those queues are coupled in a way that those queue depths better be similar. Otherwise, it's not going to make any sense, right? That's the kind of thing I'm talking about. Um, a lot of times parameters aren't truly free variables, right? Where like one parameter needs to be greater than another parameter or equal to another parameter. So recognizing these relations between parameters can help you greatly shrink that search space, right? And like I said, things like throughputs, right? If I have double the consumption throughput as the producing throughput, that's not going to make sense, right? They should be matched, right? And also, once again, you'll find that some parameters are more impactful than others, right? Some parameters really change design in a hurry. really change the resource costs in a hurry, really change the performance very quickly. Um, and so as the results, those are the ones you want to um, make sure you address, right? And so you want to do the big ones first, small ones second if you can. Cool. Questions so far? Okay, so let's say you've done your best, right? You've shrunk number of metrics down to what's a reasonable set. You've identified the parameters and what the relations are, but even still, you have too many combinations to fully explore. What can you do? Well, this is an entire research area, right? Like this design space exploration or DSC. People have entire papers and theses on how can you explore this, right? And I don't think this problem more formally, it's a non-convex optimization problem. In other words, if you have one design point and you evaluate it, and then you try to go to a better design point adjacent to it, you can improve. And you can keep following, adjacent design points to get the better design points. Do something like hill climbing or effectively gradient descent, depending on what you want to think of it as. But you're not guaranteed to reach a global maximum. You can reach a local maximum, right? So that's the challenge, right? And so normally brute force is not tractable. If it is, you can just do that and not worry about it. And so the question is, what can you do? Um, so there's a variety of choices. One is, of course, take advantage of your knowledge of the problem and use some human guidance. You can think about how to best explore design space. So perhaps you know which parameters are most impactful and you want to solve those high impactful parameters first, and then you can solve those and then kind of procedurally then solve the less important parameters and kind of hope that that leads to a pretty good thing. There are some classic algorithms, things like branch and bound, programming, randomized search. These are all exist. They are out there. You can use other frameworks to help you do these. You'll need to write these yourself. One advantage of having something like Chisel is you can plug this into not just more Scala code, but even other code altogether. Another code could call your Scala code to generate these various design copies. So those are classic algorithms. There's actually more sophisticated algorithms in the research, things like genetic evolution. Of course, machine learning is really huge. I wouldn't be surprised in a few years if a lot of DSC is done by machine learning, etc. So uh, a natural question some might ask is, gee, if it takes so much effort to generate a design point and then evaluate it, could I somehow avoid that? The answer is maybe. So this is a whole bunch of research and design inspiration, and how can I make some sort of lightweight model? And that model is so lightweight, I can, quickly explore design space and then perhaps get close to the right design, and then maybe use the heavyweight full designs to do the actual work. This approach of having this lightweight model and evaluating the whole design space quickly and then trying to like zoom in, that's a more common classical approach, and I don't think it's totally wrong, right? Part of why I did this in the past is because before you had something like a generator and Chisel, you couldn't write very many design variants, right? Writing each design variant took a lot of freaking effort. With Chisel and the knobs and the parameters, we can more easily generate variants, but even still, this problem of exploring design space still exists. When using these models, it can be helpful, and really the utilities approach is how accurate is that model, right? If the model is reasonably representative, then great. You're doing this much more productively, much more cheaply. If the model is not very accurate, then you're not getting very much, right? And so part of the challenge is that when you use these modeling, right, you may not know how accurate it is. And so how do you know how well your model's doing and how well it could do? So you often do a little bit of column A, a little bit of column B, right? You try out the model, see what it tells you, try out your real designs with your generator and evaluate them, and then go back and forth, and then see how it kind of comes together. Cool. Questions? Okay, so let's say, as you know, you've already heard in this class, you want to write a matrix multiplication unit. We did this for homework 4. People doing this for their projects. So if you want to write a matrix multiplication unit, you're doing a DSC, design system inspiration, what do you consider? Well, these are things we just talked about, right? What parameters do we have available to us? We have things like visible externally, like what problem size matrix we take and how much flexible that problem size is. Things like performance, like, how fast it's supposed to go, how is the interface set up. But then, of course, we have internal parameters, which aren't fully visible from the outside. Things like the architecture. Am I doing a 1D operation at a time, 2D operation, systolics, another technology? How am I arranging my buffers, scratch pads, caches, etc.? Parallelism. So you can kind of see already what's externally visible versus what's internally probability, and they're all still parameters. There's a zillion parameters, even this seemingly straightforward linear algebra kernel. And then for metrics, of course, we have PPA, great, power performance area. So then how might you go about this? Well, first you might specify the problem and make sure if your application makes sense. Okay, like what are the constraints I have in external parameters? I know any solid matrices of a certain size. I have a certain flexibility in terms of how those sizes can change. Figure out how to implement this. Am I targeting ASIC, FPGA, based on the problem size and the resources I have available? Do I need off-chip memory? What kind of off-chip memory, etc. Then, you know, maybe you will use some analytic models to try to help you with the modeling a little bit, right? You can kind of do things like back in the math, see, okay, I want to reach a certain throughput. I know how many math operations I need to do to reach that throughput. Can I fit enough of those hardware components on the chip, right? You don't need to write chisel to figure that out. You need to do some back end math, maybe with a spreadsheet, and see, wait a second, am I going to fit everything on chip? Am I going to hold enough SRAM to hold the matrix on chip? If yes, great. If not, doing off chip memory. So you're kind of already getting some coarse grained intuition about your problem as you're kind of going through this procedurally. Then you're going to implement the most promising design, get it working. Some way to evaluate it. In other words, turn the knobs and be able to get metrics out of it. In other words, to get, what is the PPA for this particular design thing? And then you start changing parameters, start tweaking parameters. And we talked about the last step about, how do you pick how you tweak these parameters? There's some, various algorithms, branch and bound, machine learning, et cetera, right? And then as you kind of do these processes, you might start learning about which types of things are looking more or less promising. Maybe you're going to change architecture to actually get new parameters or change architecture altogether. Learn from these things and keep repeating. So it's kind of this iterative agile process that we keep talking about this entire course. How can you go about doing that? Cool. Questions? So um, let us consider how to explore these trade-offs, right? So we talked about what happens when you want to optimize more to one metric at the same time. That's called a trade-off, right? Where you have a change in metric A versus metric B. One really important concept, which I'm taking opportunity to teach in this course, is something called a Pareto frontier. So let's say we have two metrics, X and Y, maybe area and power, for example. And in this case, we want these metrics lower is better. And so we define something to be Pareto optimal if, in order to improve one metric, I need to make another metric worse. So, for example, the point I've highlighted, I can do better at metric X, but if I do better at metric X, I'm now going to do worse at metric Y. Likewise, to do better at metric Y, I'm going to do worse at X, right? So, in other words, a point is Pareto optimal if getting better in one metric requires doing worse in other metrics. So in this case, you can imagine you had a design, you ran it through your tool flow, and you took all the various design variants and plotted them based on these metrics. And you can see that there's this Pareto frontier, and that is these are the set of points that are Pareto optimal, meaning that if you're in one of these points, you can't do better on a metric without doing worse on another metric. If you're not in the Pareto frontier, let's say you're over here, or actually maybe here, if you pick a better design, you can do better at X at no consequence to Y, right? So you should do that. There's a no-brainer. It turns out when you get more familiar with a problem, you start getting better at it, eventually you better find your way to this Pareto frontier, right? If you're an engineer. And so on this Pareto frontier, you're in a situation of, your boss tells you, I want you to improve this. And you're like, sure, I can improve this, but it's going to cost you this, right? If you can get told by your boss, I need you to do better on X, and there's no cost to Y, that means you were not on the frontier. That means you were just had a design point. Um, so these Pareto frontiers, this kind of analysis is very common, and this is the one advantage of having a generator-based methodology. If you only are able to generate a few points, right, you don't know where this frontier is or how close you are to it. If you can generate 30 points, you'll start to see these shapes, and you can start to see how you're doing relative to it. And you want to make sure you're on that frontier. And you can figure out, do I want to be here or here, right? You can figure out between these two metrics, would I rather be quite where I want to be? But the point is you want to be at a place where, it's trade-offs, right? If you're not doing trade-offs, that means you're not at the edge. Cool. Questions? Let's see some examples. So I took some pictures from papers. And so here's one, I think it's one the pretty ones I've seen in a while. And so this is a person that used a Windows model system. So they made a lightweight model to do matrix multiplication, and then they generated a zillion variants and evaluated them. And so you can see here's that same shape we were talking about, right? Where in this case, they have performance as time and power as a two metrics of both the P's of PPA. Lower is better for both. And you can see that, yeah, there's a Pareto frontier, right? It has that curved shape. For some reason in practice, it's often that curved shape. um, you can see that, most design points are not on that curve, right? They're in the middle, right? And so, assuming these are the metrics you care the most about, you don't want one of these points. You want to be on this freaking frontier, right? Um, and so, yeah, you can see that, for a given, design point, if you're over here somewhere, yeah, you can find a better one that's improving both metrics at the same time or one metric at a time. But once you're over here, then you got to trade it. So the particular plot is colored by, the level one cache bandwidth. You can see that, in the case of having very low bandwidth, you can see some of these other optimizations to kind of provide benefit, but fundamentally, you're going to want to be on the points on this frontier, right? You don't want to be over here. Cool. And here's another example. This is another academic paper. Um, and they're showing for different processor architectures how they're doing. So in this case, the curve shapes are different because the metrics are a little different. In this case, performance is better going to the right. So higher is better because they did the inverse of latency. So it's million instructions per second. And then energy, lower is better. So you have lower is better this way, higher is better this way. So you get the curve now flipped around the horizontal axis, right? So, and what's interesting in this case, you can see these lines trace a particular process architecture, in order one wide, out of order two wide, and then they sweep different frequency scales. So for a given processor, they do DVFS and show, okay, if I change the frequency, it's going to change performance. And of course, if you change the frequency, you can also change the voltage. As a result, changes energy cost, right? So you can see for any given processor, it sweeps that curve. And what's interesting is, depending on what your performance target is, for example, the most efficient processor changes, right? And the progression actually here is very satisfying architecturally. It makes sense, right? If I have a very low performance target, a one wide in order is going to be the most efficient, right? That makes sense. It's the simplest design. It's not nothing. And then if I need a little bit more performance, a two wide in order is pretty good. Then you can see that as they increase performance more, there's an interesting regime. So there's a small regime here where actually four wide in order makes sense. Additionally, if you want more performance still, then you of course want two wide out of order, finally four wide out of order. You might notice that, for example, one wide out of order doesn't win against in this scenario, right? At no point for its curve does that make sense, right? And you can kind of take insight from that. Okay, yeah, that makes sense. If I'm going to spend the resources for out of order, um, I would probably rather actually build either a smaller in order core or even a two wide in order core or something, right? And so, like I said, these Pareto curves come up throughout engineering, and you have to make these trade offs, right? Like, where am I going? I'm improving one at the other, expense of the other. And so, unfortunately, for the project, it's a little bit hard to explore this. We don't have a cost model for your designs, but even for performance, you can still play with this, right? You can still kind of turn the knobs a little bit. And there's also more just good for your careers. You'll be seeing this for sure when you do real designs in the industry. Great. Any other questions? Okay, let's